I've I've written the book Rust Web Programming, so it's the first textbook in this, and the new book that's coming out is speeding up your Python with Rust. So it's kind of like how we build pip modules and import them into Python and run them just like Python code, but they're in Rust and they're faster. I used to be an A&E nurse, and then I went and studied physics, and then went into R&D and financial tech, and then went into Monolith.ai and then OasisLMF. So I'm just going to talk a little bit about OasisLMF as well. So Oasis is a loss modeling framework. We're an open source foundation. And right now, if you do catastrophe modeling, there's only really two companies in the world that kind of do that. There's a duopoly. So we have a platform that kind of enables people to build risk models for, disasters and weather events and that sort of thing. And it enables, third world countries and smaller companies and stuff like this to access it without having to pay huge fees to these massive companies. And this is the sort of stuff we do. It's kind of has an interface and works out hazard and stuff like that. And we're also working on open data standards, so we can actually have more transparency, and you're not going to get locked into one, platform, and your data can go to another model provider and that sort of stuff. So it is all open source. I highly recommend you check it out if you're interested in open source. I think Oasis is one of the first ones in insurance to go take advantage of Docker and that sort of thing. So we're always looking at cutting edge things as well. So it's kind of like a for good organization, open source, and we usually are doing cutting edge things. So going into what we're going to do, we're going to talk about Rust in web development, and we're going to go over to a basic TCP server with Tokio, and we're kind of rewriting Redis, but we do a very basic version of Redis. Then we're going to upgrade it to a HTTP, still with Tokio, and then we're going to go into more higher level stuff. We're going to go into like Attix web middleware, and we're going to go into like even more higher level, which is the Rocket. So first of all, we'll talk about why we use Rust in web development and why is it growing and why is Rust so popular. And this really caught my eye. I think it's a couple of years ago now, and this is Discord, and they're mentioned why they switched from Golang to Rust, and the spiky purple ones are what happened with their Golang servers, and then this is what happens when they switch to Rust. And it's because Rust doesn't really have a garbage collection, so it has a very aggressive memory management system that just chops everything off that goes out of scope. Now you can use stuff like borrowing and that sort of thing, so it doesn't mean that everything you write will just be chopped instantly, but what it does mean is that you pay a tiny transaction fee every time, so you don't get build-ups and you get very smooth, predictable behavior. And this is also another benchmark that was done by Jamil Chowdhury, and he used these to kind of like have a a standardized server, and he tested them against Flask, Falcon, and the Attix web and the Rocket are the ones that are written in Rust. And as you can see, the total requests are huge compared to like Flask and Falcon and Nest. Requests per second, all this, it's just not even close. This doesn't mean that you should ditch Golang. I haven't actually, I'm sure there's some comparisons out there, and I've also heard that Golang, because of its Go routines, can sometimes beat Rust in some of its connections. So I'm not going to be flexing Rust all the time and saying that absolutely everything is terrible compared to Rust. Obviously do your own research, and depends on your use case. But we'll also go back as well, and these are some of the benchmarks. And as you can see here, we got C++, which is kind of at the top. You see these languages, and then kind of Rust dominates up here, and then you kind of go down, you get more of them down there. And again, speed isn't absolutely everything. There's other things that will make you pick a language or something like that. And these are the borrowing. So some of you are mostly coding Rust, but if someone's just curious, these are the sorts of things that kind of enforce kind of memory safety. And there's a kind of rite of passage with coding in Rust, and it's called fighting the borrow checker. And they have a very comfortable, very useful, helpful kind of compiler, and it'll tell you where you're going wrong. And you can't, like, if you can't guarantee a lifetime, or you've done a mutable borrow and then you try to borrow it again and stuff like this, it will just fail to compile. And this is how you get the memory safety in terms of that. So this is quite a useful graphic. I just recommend, if you're new, just try and understand, these sorts of borrow rules, and then Rust will be a lot nicer to code with. And there have been some talks that I've seen where people have rewritten C programs in Rust, and they're actually faster. And it's not that if you compile Rust and C together on exactly the same code that Rust is faster. I'm sure C is faster. It's that you have these kind of rules kind of beat you into writing good code that's kind of safe. So this is why we kind of love Rust, or why I love Rust. So we have no garbage collection, yet it's still safe. It forces you to write good code, and you work at a level that you're comfortable at. And this is something else that we'll explore throughout the talk, because we'll do the different levels, and you can see that we can kind of explore all different types. And it's also static binaries, which are also nice. They're a lot less, in terms of like size and stuff like that. So first of all, we'll write our TCP app in Rust. And for those who are not too familiar, TCP is actually just below HTTP. And then if you look at the security, the HTTPS, you have a security layer before you get to your HTTP. So we're going to start with TCP. And if you look at some network apps and databases and so on, they generally do use TCP in that sort of stuff. There's less overhead, and you kind of, it's a kind of a raw implementation. And we're going to use the Tokio, and the Tokio API is really simple to use, but it's also very powerful. It's very fast, reliable, and it's easy. And this is where you only have to use it. You only have to decorate your main, function with this, and you turn it into an asynchronous server, which is quite impressive. And this is kind of like the stack. So Rust is quite modern, and we've learned a lot about software engineering, before Rust came about. And a lot of these open source frameworks, they kind of play off each other, and they make it very obvious. So this is taken directly from the Tokio website. This is just a screenshot, and they all know where they all kind of stick with each other, and they all kind of interplay with each other. So you can like jump in and out of these different frameworks and go to a higher level or a lower level quite easily. And as you can see, we're going to start using the IO, the runtime, which is kind of like a file system synchronization. You can do scheduling facilities, that sort of stuff with this. But before we go further, because we are going to implement a very basic implementation of Rust, this is not going, Redis, sorry, this is not going to replace Redis. Obviously, Redis has a lot more input. They have a team, it's written in C. Their Redis JSON has been recently written in Rust, but this is kind of just for educational purposes. If you want to just use Redis and, just store stuff, key values, then I'd recommend just using Redis off the shelf. We also have to realize that if we're going to use Tokio, there's some things that it's not a silver bullet. It doesn't solve absolutely everything. So if we have something that's very high CPU, like a very intensive parallelization, we should really use Rayon. And here is an example on the right of how we use Rayon. It's quite an easy way of just looping through and mapping a function. Or if we're going to use a lot of reading and writing of files, so if we're going to read and write a lot of different files, the asynchronous sounds like it's a good idea, but sadly, a lot of these operating systems don't actually provide asynchronous API, file APIs. So I don't know all the ins and outs of every operating system, but this is just generally a thing. So you most probably won't get any gain there. And if you're just kind of sending one request, this is an asynchronous runtime. So there's one called request. It's kind of spelt, REQ, which you can use, which is great for that. So we're going to set up our initial environment, and this is pretty much all we need. This is like a network application. As you can see, we use Tokio and we use a version, and we have to have the features of them full. Otherwise it gets very strange and you get some very unhelpful error messages. And there's this other one, the crate that we're using called slices array. And it's a small crate, and all it does is really convert a slice of what you get into an array. And it sounds very simple, but in Rust, it's quite hard. So this kind of small crate is a bit of a lifesaver in that sense. And as you can see in our main file on the right here, this is where we import all our stuff. So we use a TCP listener. We're going to use some traits in the IO, which is like read and write. And we're going to use the arc and the mutex because we're going to have a hash map that's kind of spread across all the threads, and we're going to access it and we're going to be exclusive to it. And then we use our slices array and we define our own value store. So for this simplistic example, this value store, we're either going to store a string or an int as the value in our hash map. So then this is just documentation on the arc, and we just say it's a thread safe reference counting pointer. This is being recorded, so you can just pause on this. We can also send some links as well at the end. So now we get to our main function, which is just also in the main file. This is all in one file. And we can see that we decorate our async main function with the Tokio main, and it returns a result. And this is where our database is. So it's our smart pointer, it's a counting, and it has strings as the keys and value store as the value. And it's a new hash map, basically, wrapped in a mutex. And then we have a listener as well, which is just a TCP listener, and it's bound to a certain port. And then we have a loop, and we accept packets that are coming in. And in that loop, we make a clone of the DB, which is just a pointer. So we can actually access this DB pretty much anywhere we want. Then the next one down, as you see here, this is further down in the loop. So we'll then spawn, once we've accepted, an incoming packet, we'll spawn a Tokio future, and we'll move everything into here. And then this is where we'll actually do the processing once we've received, the data. So what we've got here is a mute buffer. And this is kind of like, it's a slice. Well, no, it's an array, sorry. And it's mutable. So we can kind of change the data inside, but we can't change the size. And it's because we're compiling, we want to allocate this amount of size. Now it's quite a big one. And you'll see later on when we print the data, there's a lot of empty space, but it's just an example again on how to actually just process bytes in the most simplistic way. And then we pass the buffer in, and we actually read what's being sent into our TCP port. And if it's nothing, then we just return it. If it is the bytes, then we return the bytes. And if there's an error, then we'd like to print out that there's an error happening because we want to know what's going on. So once we've got that, just before we go a bit further in code, we'll just make up our own protocol, which is a very simple protocol. So we'll have one 4-byte integer, which is the operation. So what type of operation are we going to do? So is it an insert? Is it a delete, or is it a get? Then we'll have a data type, which is just another 4-byte integer. And this will be, if it's 1, we'll say, okay, the data that we're passing in is a string. If it's 2, then we'll say, okay, the data that we're passing in is integer. Then we'll allocate some of the buffer to a key, and we'll allocate some of the buffer to a data. So the data that we're actually passing in. And this is kind of like what it is. So you can see here that we get our array as slice, and we get the first 4 bytes of the buffer, and then we convert it to an int 32. And that's how we actually get our first operation. And we do the same with the data type. And then we do the same with the key. And we know that we've given it an arbitrary 20, a slice here. And then with the data type, we then match which one it is. So if it's 1, then we do 400. We've allocated 400 for a lot of text data, and we convert it into a string. If it's 2, then we only get the first 4 bytes because it's going to be an integer. Sorry, if it's 2. And then we put that as a value store in the enum. So we process all our data from the packet that's come in. And then we match, and we start to do some things. So this is a very simple, I wanted to make sure that, I ran through the presentation multiple times and it made sense. So I only wrote one function fully, but the other 2, you get the idea, right? So the first one, we've got an insert, and then we get our database, we pass in our key, and we pass in our value. And if you can see here, this is outside our main function. This is our insert. And we've got the database again, we've got the key and we've got the value. And then we get a mutex guard. And we get this from, locking our database. So that means that nothing else can really access this hash map whilst we're doing this transaction. We then insert the key. I print it just for the console, just to show you. I mean, we can do write all, as you see at the bottom, at the top here, where we do this error. We can also do at the end of this insert, we can write in a socket, we can pass it in. But this is just to show you how to do an insert, and then we're just going to print it out. Now you notice that I don't unlock it, and that's because we've got, again, Rust's way of managing memory. It will just cut it anyway. It will drop that mutex guard, and the database will just be automatically available to the next one, the next transaction. And that is it. That is how you've actually got the nuts and bolts to do a Redis implementation, a very rough Redis implementation, but it works. So this is quite impressive, right? We have all this concurrency with the Tokio. We have complete lockdown, and we get no data races, and we get no data corruption with the mutex. And it is just a hash map. So we can go on to packaging it. And this is where it gets really cool. So we get the Rust, image. We copy in our data on our cargo toml, and then we do a cargo build. So we say what the work directory is, and then we do a cargo build release. But then we notice that our Rust is as a builder. So we're going to use that later on, because Rust, this version of Rust, is actually built on the Debian Buster Slim image. So we get a new image, which is just, Debian with no dependencies or anything like this. And we copy from builder our release, and we put it into our new Debian image with no dependencies installed or anything. And then we just change we make, sorry, I'm blanking a bit. It makes you, the cmod, we allow, the system to run it. And then we expose the port, and then we actually run the network application, and it runs. And when you look at something like this, because we're only transferring the binary over, and the image has absolutely zero dependencies, it's just a Linux, the whole image is only 72 megabytes. And this is very different from, let's say, if you wrap a Flask application, it's usually over a gigabyte, because you've got to have the Python interpreter, and you're going to have all these dependencies and all this sort of stuff. So you have very fast servers that you can build, and they have a fraction of the footprint as well. As we saw with our benchmarks, some of these were going over 1 million in terms of the connections, whilst our Flask was bottoming out at 11,000. So this is just a massive improvement. And I mean, I'm taking a bit of a dig at JavaScript here, but if anyone's really coded in JavaScript, I don't hate the language, but the node modules, as anyone can attest, are just huge. We compare that to our 75 or 72 megabytes. It's just it's a really lovely, way of coding. And I guess this is maybe one of the reasons why so many people love coding in Rust, because the packages are quite clean. We've learned a lot from the mistakes, and when we compile everything, it's super small. So we can build our client, and this I'm going to pick in Python just to show you, just to mix it up a bit. And this is how we create our protocol and how we send it over. So we have a few enums, and it's the string and int and the operation here. We get our TCP port, our buffer size. We encode our key, some key, it's whatever it is. And then we've got some dead space because we're taking the slice. So we have to fill up the dead space with nothing, which is a byte array. And then we do the same with the message, and then we have to put in the dead space as well. So we will get some, dead space, but this is how we actually have our own protocol. Then we connect to our socket, then we send our message, and I've commented out, but I've left it there. This is how you receive. So if we're going to send something back, you'd receive this, and we'd have to do a write, and then we close. And this is what you get in the database. Now there's a lot of empty bytes there, and you could trim them, but I kept them there just to show you what's actually happening under the hood. So we've got some key installed, then we've got a load of empty bytes, but you can see at the right slice, then we've got a string and this is a message. So our calculations were correct. We're slicing it just at the right time, and we can work out what type of operation we want. And this is pretty crude, but it does work. And if you have numerical data, you can have structs and that sort of thing. With numerical data like rows in a CSV or something like this, you can be much more tighter with your buffer because you know exactly how many bytes is in an int and how many ints you've got and all this sort of stuff. So it's much nicer. Strings are obviously very variant, which is why you have so much loss there. And then we go further. So this is kind of like on the same thing. So Tokio has this thing called framing. And this is kind of like a layer where you get a byte stream, you convert it into a stream of frames. So you can send multiple packets and they can convert them into these enums. And if you can see, we've got a very basic one on the left, but on the right, and this is taken directly from the Tokio documentation, you can see how the HTTP basically comes from the TCP. So we can go one step forward and we can actually start to build our own HTTP. And we also talk about, this kind of gives us an insight into what the difference is between HTTP1 and HTTP2. So HTTP1, we used to have multiple TCP connections. We used to send one thing at one time. However, if we go back here, we've got the request head and all this, but there's nothing stopping us from putting a unique ID. So we can have multiple channels. So you can send multiple different requests down one TCP connection. And if you're mapping the correct unique IDs on the other side, then you're not going to get confusion. So that's how HTTP2 was, when you could send multiple different requests under one connection. So it gives us a lovely insight into really the evolution of HTTP and how it can really come about. But we don't really want to roll our own, right? HTTP is already well established. It's nice to do it as an educational exercise to appreciate what's going on. But in production, why would you really want to do your own HTTP protocols? And that's where Hyper comes in. And as you can see here, this is just above the Tokio runtime. And it's pretty much the same thing. But I just import, as you can see, a load of stuff from Hyper. So they have their own server, they have their own body, they have their own request, response, status code, make service function. And we're still using the ARC and the mutex. And we also use another one called Sarray JSON. So we're gonna process the data. And as you can see, it's pretty much the same, but instead we get a socket address. We still get our hash map that's the same here. And this is a vector of strings. This is taken from another project that we did. And then with the server, we bind and we serve, and then we move in. So we take a clone of the database, as you can see, then we do an async move, and we move our service function. We call our service function, sorry, and we pass in the request, which also has a handle, which is what we're going to code. I'll show you what it is. And it passes in our request in our database. And as you get a feel, right? This is just one step above the Tokio main, the Tokio, right? So this is our handle. As you can see, we pass in a request body, a database, and then our body has 2 bytes, and you can unwrap it. Our string body, 2 bytes to vector, and then we get a Sarray JSON, which is going to be a Sarray JSON value, and it just says from string, and you can just serialize, your JSON body. And then you can do whatever you want. You can see we're doing this lock and we're doing some things to it. And then at the end, we can get our raw data. So this was patient data at the time. We're building a patient cache that trained chatbots. And our response builder, you can just build it and then send it back and return that builder. You have status codes and all that sort of stuff. So you can see that these are just wrappers really around TCP protocols. But obviously it does a lot of heavy lifting, and there's no point, you doing that yourself. And then we go one step higher. So we can go to the Attix. And this is something that I keep reading about actors, and I wish I could confidently tell you that I fully understand it, and I don't. But really, I've given you this demonstration here to show you that you've got your Tokio core, and then they pass on messages to these actors, and these actors are kind of like, it's kind of like a message protocol. So this is just another layer, just kind of on top of the Tokio. And this is where you get to Attix. So if you can see here on your left, we get your Attix main, which is kind of like your Attix messaging. So it's just kind of, again, that layer above the Tokio. And we import a load of things. And I can point you to where this is, because this is from the book. So and Pacti have the GitHub of all the code on the book. So I can point you to this actually, and we can send this later if anyone's interested. And you have a new server, and what you can do is you can wrap your function. You can start to write middleware. So what this middleware kind of does is, I kind of built an authentication token, and then you try and deserialize it. And if we move to the right, then we either go down, we call the request, or we return a response saying that it's unauthorized. So you can kind of do things. It's still a bit low level. So what you can do with this is that you can start to interact with things before the HTTP, before you actually call the actual view. So it kind of protects, against certain attacks and so on. And you can do this with Hyper and so on as well. But Attix is just it's a really nice framework to actually play with. And then we get to the really high level, which is Rocket. And this is where you can kind of see, if anyone's coded in Python Flask, you can kind of see huge similarities here. So on the left, this is how we define our actual views. And on the right, you can see at the bottom of the main, you don't even have to wrap anything in the main function. It's got a Tokio ignite, and you start to just mount your stuff. And you attach a DB connection. And on the top right is what you'd import. And Diesel is kind of like the ORM, where you'd map to your database. So as you can see here, this is literally just like Rust, just like Flask. And if we look at the get items, you can see in the left, we have a DB connection and we have a token. And this is where this gets really cool. All that kind of middleware that you saw, and it looked a bit headachy, you can build your own struct. And in tokens, so this is here, you can see on the left, the JWT token, which is a struct I made, I can actually get the from request, which is already built in to Rocket. And the from request gets the request. And you do a few things. So you can see I'm doing exactly the same thing here. I'm getting the token from the header and I'm decoding it. And if it fails, then I'm going to say, look, it's unauthorized. Whereas if it's okay, and I'm going to say the outcome is a success. And this kind of just guards. So this stuff automatically happens and becomes initialized before you actually get to the view. And if you look at the top right, Rocket Contrib has already done all that hard work for the database connection. So it already mounts the database connection, all this. So if we go back to our get items, you already have a fully connected database with all the params, and you already have a fully authorized token with the user ID and all this sort of stuff based, just automatically passed in. So this kind of framework is, really high level, but really fun. And Rocket was the one on the framework that got over 1 million connections on that benchmark. So it's still really fast. So even though you're playing with high level code and your code kind of looks like Python, it's not really anything that's too heavy to get your head around. You still got that really fast, high performant code that's kind of working. And this is kind of like where we're at the end. I kind of rushed through a bit. I've talked a bit faster than I should have, most probably. So I guess maybe there'll be some questions and say, can you please explain something a bit better? I would say, and this sounds quite hyperbolic, we can all roll our eyes when somebody says a programming language is the future. And if you look at Medium, you can happily see people saying like Python is dead, or Julia is the next language, and everyone's going to be coding in Julia, and all this sort of stuff. And most experienced developers kind of know this is just not, this is just not going to happen. But with a few technologies, true revolutions do actually happen. And we can see this with Docker, right? We can see that Docker revolutionized development. And the reality of that was that if we look at the value, it's because Docker kind of tore down the wall between operations and developers. So developers had to try and get new features out, and operations had to keep things running. So developers would try and do something cool and quick. Operations kept pushing back because they don't want to break their systems. And what Docker did was it brought about DevOps, which is where your developer can just do a local, can run it all in Docker Compose, can test stuff. And I'm sure none of you batted an eyelid when I talked about optimizing the build in our Docker file. So even though I'm a software developer, I'm also thinking about how it's deployed with my Docker file. And this kind of just accelerated everything. And I think this is the same with Rust, to be honest. I think there's very few times does something come around that's very big. And I think that's why Rust has been the most favorited language, 6 years in a row, is that it fuses developers with systems programming. So what you saw was with Tokio and the TCP listener, you could build something that's highly concurrent, that's memory safe, that takes a fraction of the memory footprint, and it just runs on a TCP port. So you can have this running in the background in another application, and it wouldn't really hurt. Or you could have it running in a service in your Kubernetes. And that was really what happened when I was developing some medical simulation software for the German government with Caroline. And what we had was we had these patients. We had these fake patients that were generated, and we had to train a chatbot based on the past med history every time they got generated. Now, we got a load of people log onto the system and it completely crashed because training chatbots for every patient, and you get multiple patients per user because they had to try and, simulate working with them, then, it fell apart, it fell over. So we reached for Rust in that sense. And that was one of the affirming moments for me with Rust, was that we built our own kind of Redis-like system that was very small, very highly concurrent, and it stored, we had a cron that kind of worked at midnight, and it kind of trained all these chatbots, and then it stored them in our Redis, kind of like pseudo Redis system. And it wasn't, it's not that we could have used Redis, it was more that we had different diseases, and then the patient was categorized under that disease. And then we had vectors where we had pointers to, and then we stored the JSON files inside the network app that was coded in Rust. And this became a caching mechanism. And we wrote it in one file, and it worked, and it completely saved the system. So this is where, like the people who took on, Docker, and you kind of got this explosion of innovation where you had these developers who were just all of a sudden starting to worry about how their system was deployed, and they started looking into it. And I remember I never looked into HTTPS or Nginx or anything like that before Docker as a software developer. And then afterwards, you start reading up on all this stuff, and it kind of fuses the worlds. I think that's the same with Rust. I think the organizations that have Python or PHP, or there's a whole range of these developers, if they had this extra tool that they reach for when they need some systems level programming that's safe and easy to use, that kind of smashes the two worlds together, and you're going to see a lot of really interesting solutions as a result. And sadly, that's the end. Hello.
All right. Is it?
Yeah.
I guess now we'll just jump into sort of questions. I guess the best way to do this is, I don't know if this has the hand up function, or if not, just shout them out. If you want to ask a question, then unmute yourself and fire away.
It's nice that some people are happy with the talk. That's the
yeah, Alistair. Yeah, if you want to.
Hey, thank you for the talk. That was interesting stuff. So you said there's the image for the Docker container 72 meg. How big do Rust binaries tend to be at that sort of size if you are like actually compiling for the native platform without Docker?
Oh gosh, that's a really good question. I never really checked, to be honest. But I mean, it's gonna be very small, I guess. But yeah, I'll sadly have to get back to you. Badly prepared.
No,
very good question.
Yeah, is it all right if I ask another question or two?
Yeah,
Right?
yeah.
I don't want to get in the way of other people that have questions. So you used pretty fixed buffer sizes there, right? How does Rust work with like user supplied lengths in packets and stuff, right? Where you need to work with buffers that are variable length based on user input. Does its memory protection mechanism start to cause issues, or like what happens there?
Yeah, so sadly that is a case. So if you start to do an alter, so you start to alter the size, and this is something that I tried to play with for the example as well, because I was thinking it would have been really cool. But yeah, it doesn't, Rust doesn't really like it because it can't guarantee the size of of the memory that's coming in. So it starts to complain. I'm sure there's some certain ways to do that. I mean, they've managed to do it with the HTTP, which is obviously going to be very variant and stuff like that. But it's something that, I don't think you could do as just jumping into it. So I thought I would just try and do the simplest form. It's the same with the frame.
Yeah, that makes sense. So the slices array function, is that creating a slice across an existing memory buffer? So the existing buffer stays where it is, but then you're representing like a subsection of that array without a copy. Is that sort of what's happening with that?
Yes. Yeah.
Okay. So it's a bit like .NET spans and stuff like that, right? Where they represent a subsection of the array. Cool. Okay. Understood. Thank you.
No, thank you. Hey, is it Alistair?
Yep, that's me.
Oh, is it? Oh, you're still focused.
Oh, right. Sorry, talking to someone else.
Does anyone else have a question or?
We got Martin Becker. He says, can you use an enum as a container to implement a form? You can call there's a thing called generics, and you use the capital T, and what it will do is that then it will look through the code and then kind of write when it's compiling all the different variants. I think that might be a bit different though with data that's coming into a TCP port, because obviously the compiler can't look through and check the different types there. So that is, one of the downsides for that. But yeah, it would be if you want to store like a range of different types of data without having to write an enum for every single one, then I would suggest just storing the bytes if you're going to use it as just a storage. And then you can have a bytes buffer, which works. And in the Tokio tutorials, they go a bit further and they actually do use bytes buffers just to store things.
Any final questions from anyone?
And then we've got Sean Trotter making the point about the size. So if anyone's interested, I couldn't tell you. Sean's told us that it's 9.6 megish, which is Stephen Trotter. Sorry, not Sean Trotter.
It's all right. It's all good.
Max, just to confirm as well, did you say you would be making some of those slides available? Because I know some people saw some slides earlier that they thought could be helpful.
Yes, yeah, I can send them to you. We can disseminate them, and then also some, as I said about the PAC-T and stuff, they were quite good at, they put all their code on an open GitHub repo as well. So I can point you to that, and it gives you the different types of frameworks that you can play with, and you should be able to kind of work out what's going on, that.
Okay, lovely. We can share that with people at the end afterwards then. That's all good.
So unless anyone has any final questions at all, I guess I just on sort of behalf of everyone, I guess, thanks very much, Max. That was great. Really insightful. Just in terms of sort of next week then, obviously we've got the second part of this sort of mini series that we're running. Like I said, that is at the Nando's offices in East Putney. So by all means, do feel free to come along and check that out. And all those details will be on the event page on LinkedIn. But there's also the expertise.nextgen group, which I'll sort of try and invite everyone to. Feel free to join. It's a big community of developers focused in London. So yeah, and I think it's also worth mentioning Max will be giving out a free couple of copies of his new book that's coming out at the next event. So that's something to really get excited about. But yeah, thanks very much for everyone for showing up, and thanks to Max for speaking. And hopefully see you all soon at some more meetups in the future. Cheers, guys.
See you later. User API. Hey mate, yeah, I'll just send you a message, I guess, and
Yeah, that'd be great. I don't know if you want to stay on for a couple of minutes, Max.
yeah, that'd be,
So,
that'd be
yeah.
good. Yeah. Still got some. I was always a bit nervous about how it comes about, right? It's
oh, did I just? I'll invite you back in. Sorry, it's always that slightly awkward time when I just have to go around evicting everyone from the room. I accidentally evicted Maddie. Do you want to jump back on? I'll admit you. That was really, really good. That was a really good engagement from everyone as well. It's nice when you got lots of questions at the end and throughout, to be honest. How was it for you?
Yeah, it's good. I'm always like worried that there's going to be someone who knows way more than me. And I'm going to say something really stupid, and then they're going to be like, this guy doesn't know what he's talking about. You know, it's it's one of those. It's the same with like the book. I haven't actually read my book afterwards.
Yeah.
I'm like, if I see a mistake, I can't do anything about it. It's in print.
No.
You know what I mean?
Probably the best thing to do is to. Oh, sorry, I've evicted Maddie for good by accident, but I'll let him jump on. So, but I just want to say that was really, really good from my side. Oh look, he's waving. Can I take off? I don't know how to take off the headset audio. I'll pass him across in a minute, but that was really, really good, really smooth as well, and it'll be a pretty similar setup next week. And what we'll do is we'll do like the food afterwards at the end. So we'll just give it a beef. Oh, actually, just a very quick one. Nando's, because they're working with Rust over there, what they would like is just before you talk is the 5 minutes for them to be like, this is all the stuff we're doing at Nando's. So I assume that's fine, but they'll kick off doing that, and then we'll just hand over to you, and it'll be exactly the same format as today. What was there anything that you'd like to do differently next week though, or any thoughts you have about that?
No, not really. Like I just I guess I should have done the readmes a bit better, for the GitHub things, but it was just time against the wall, and hopefully next one will be a bit longer, because this kind of cut short a bit, I guess. Because you guys kind of want an hour, I guess. That's the. Well,
I'm always of the view quality, not quantity. If it finishes before the hour, but it means everyone's super engaged. That to me, that's fine. Because I've been on either end of the spectrum when we've been at meetups which have lasted too long, and you could feel that people are just like, I'd done. So I thought this was really smooth. It felt very, it came to a very natural end. It wasn't like we were forcing anything. So I thought that was good. And the other thing as well is probably with Nando's little talk as well, it probably will just come to an hour. So my point is just don't worry too much about it. If it's not quite an hour, that's absolutely fine. Because what we will have afterwards is the food and beers and stuff. And actually what we do tend to find is there are a lot of people who don't like asking questions in front of the group, but they like to come to you at the end and ask you personally. And it's nice to have time for that as well. If that makes sense, Max. So yeah, I wouldn't worry too much about that. But I'll let Matty say bye.
All right, Max. Sorry about that. I ended up getting ejected pretty early, but no, yeah, I just wanted to say massive thanks, really. Really enjoyed the talk, and yeah, well, thanks for making it possible, really. Look forward to meeting you in person, I guess, next week, over at Nando's. We'll be 4:30. Yeah, 4:30, we'll be there from about 4:30 to sort of set things up and stuff. So I don't know what time you want to arrive, whenever you want, but just quickly on that, are you going to bring your own laptop, or are you going to send some stuff over? Would you like us to?
Oh yeah, I can bring my own laptop, because then I guess if someone wants to talk afterwards, I've got like some programs on there that I've coded, or you know what I mean. It's always good, I guess. You can show them what you're working on and that sort of stuff. Okay, great. So we'll get that sorted. And then I guess just throughout this week, if you need anything from any of us, reach out. And yeah, I look forward to the next one, really. No, thanks for your time. I appreciate it as well. Yeah, no, thank you. It's been fun. I don't know. Did you want to say anything? No, that's it. Yeah. Just see you next week. Yeah, well, I'll be in contact throughout sort of next week to just make sure everything's okay. But yeah, thanks very much. Right. See you later. Cheers. Catch you in a bit. Bye. Bye.